Okay, let's dive in. Recurrent neural networks, RNNs.
Right.
There's something, well, almost magical about them, wouldn't you say?
Oh, definitely. I remember that feeling too, seeing those early results, like image captioning from fairly simple models.
Exactly. It felt like, how is this even working? Especially because, the word was they were super hard to train.
Yeah, that was the initial reputation, but maybe that wasn't quite the whole story.
Turns out, maybe not. So the really key idea here seems to be processing information um, sequentially
Hmm.
over time.
That's it. Remembering what came before to figure out what comes next. It's that temporal aspect.
And that initial surprise you mentioned, it really shows how, well, our intuition sometimes needs to catch up with what these things can actually do.
It was a genuine aha moment for a lot of people.
Yeah,
Feed in a sequence, get something sensible out. That was big.
right. So for this deep dive, we really want to get under the hood. How on earth can an RNN generate text, like character by character?
Hmm.
I mean, seriously, one letter at a time? How does it decide the next letter?
Okay, good question. And to get there, we need to contrast them with, say, your standard neural nets, vanilla networks,
Hmm.
or even CNNs.
Right, the ones that take a fixed size thing, like an image.
Exactly. Fixed input, fixed output, maybe a classification label. The number of steps is fixed too, usually just the layers.
Like processing snapshots one at a time, static.
Precisely. RNNs break that mold. Their strength is handling sequences of vectors.
Sequences.
So that could be a sequence in, like feeding words for sentiment analysis,
Uh-huh.
or a sequence out, like generating an image caption word by word,
Gotcha.
or, sequences both in and out. The machine translation is the classic example.
Like English in, French out, word by word. Well, roughly.
Yeah, or even sync sequences, like classifying frames in a video, input sequence, output sequence lined up.
Okay, so it's this flow over time. And the neat part is it's not rigid about the length. Short sentence, long paragraph, it can handle it.
Theoretically, yes, because the core operation, that recurrent transformation, it's fixed. It's the same function applied over and over again,
The same function.
which lets the network sort of keep a running memory of what it's seen.
Okay, now this is where my mind goes. A fixed function applied repeatedly using some internal memory. That sounds like a little computer program running.
That's actually a really good analogy. You can think of an RNN combining the current input with its internal state, using this learned function
Uh-huh.
to produce the new internal state. So yeah, people say RNNs describe programs.
Right. And I read they're technically Turing complete, which sounds
Mhm.
impressive, but maybe a bit theoretical for now.
It is impressive theoretically. It means they could simulate any program. But yeah, let's maybe not get too bogged down on that. The key shift is optimizing these sequential processes, not just static mappings.
So training a normal network is like finding the right function map, input to output.
Right.
Training an RNN is more like finding the right program, the right sequence of steps.
You got it. It's optimization over programs, not just functions. Finding the right state updates to get the desired sequence output for a given sequence input.
And this isn't just for sequence data, right? Those DeepMind examples were wild. Reading house numbers by scanning, generating digits by painting them step by step.
Exactly. Even with fixed data, like an image, you can design models that process it sequentially. They learn stateful programs even for fixed size inputs. It really opens things up.
Okay, so strip it down. What's the basic API? What does an RNN look like from the outside?
Super simple. At its core, feed it an input vector, get an output vector. But the key is that output depends not just on the current input, but on the whole history of inputs it's seen.
Ah, the memory thing, like it's got a little notepad.
Sort of, yeah. Think of it as having an internal hidden state vector.
So hidden state, okay.
Every time you feed it an input, it calculates an output and it updates this hidden state.
Mm-hmm.
And that update uses both the new input and the old hidden state.
And this update, that's the step function.
Correct. The step function takes the current input, let's call it x at time t, and the previous hidden state at h at t1, and computes the new hidden state, h at t, and usually the output, y at t.
And how does it compute that new hidden state in a basic vanilla RNN?
Okay, so mathematically, it's usually something like take the previous state, ht1, multiply it by a weight matrix, let's say y.
Hidden to hidden weights.
Yep. Then take the current input, xt, multiply it by another weight matrix, yx.
Input to hidden weights.
Right. Add those two results together, maybe add a bias term too. And then critically, you squash that sum through a nonlinear function, often tanth, the hyperbolic tangent.
That keeps the values in a certain range.
Exactly. Typically between 9 and 1 and 1. That result is your new hidden state, ht.
So it's mixing the past, old state, and present input, transforming them, and then squashing it.
That's a good way to put it. And the output YAT is often just the new hidden state HT multiplied by another weight matrix, Y, hidden to output.
Okay. And these W matrices, YET, why those are the things the network learns during training.
Precisely. You start them off random. Then you feed in data. Look at the RNN's outputs. Compare them to what you wanted it to output using a loss function.
Like, how wrong was it?
Yeah. And then you use backpropagation to figure out how to nudge those weights. Why did I see it? Why to make the output slightly less wrong next time? Training is just finding the weight values that minimize that loss over your training data.
Got it. And like other nets, you can stack these, make them deeper.
Absolutely. You can have a multi-layer RNN. The hidden state from layer 1 at time t becomes the input for layer 2 at time t.
Yeah.
Lets it learn more complex stuff.
Okay. Now, the source mentioned that this vanilla RNN, it's maybe not what people use most in practice, something called LSTM.
That's right. Long short-term memory networks, LSTMs. They're kind of a souped-up version.
Souped up how?
Well, the core idea is the same recurrent connections, hidden state updated over time. But the way the hidden state is updated is much more complex. It has these things called gates. Yeah, input gates, forget gates, output gates. They help the network learn what information to store in the hidden state, what to throw away, and what to output. It makes them much better at learning long-range dependencies, connections between things far apart in the sequence.
Ah, okay. So they have a better memory, essentially. Less likely to forget important stuff from way back.
That's the intuition, yeah. And they help with technical problems like vanishing gradients that can plague simple RNNs during training. So just know that while we talk about RNNs conceptually, the experiments we'll discuss mostly use LSTMs.
Got it. LSTMs are the workhorse, but the core RNN idea holds. Okay, so back to the main event. Generating text, character by character. How does that training work?
Okay, so you train it as a character-level language model. You get a massive text file.
Like War and Peace or something.
Exactly. And you train the RNN to predict the probability distribution of the next character given all the characters it's seen so far in the sequence.
So if it sees THE, it should predict or if it sees QUICK, predict A.
Well, it predicts a probability for every possible next character in your vocabulary. Ideally, the probability for the correct next character in your examples should be the highest.
Ah, okay. So it's learning likelihoods. How do you set up the training examples?
You take your long text and slide a window. Let's use a tiny example. The word hello with the vocabulary of just HELO.
Okay.
The first training example is input H, target E. Second, input he, target L. Third, input hell, target L. Fourth, input hell, target O.
So each position gives you an input sequence and the very next character as the target.
Exactly. And you do this for the entire massive text corpus, millions of examples.
How do you feed H or he into the network? Vectors, right?
Right. We typically use one of K or one hot encoding. If our vocab is HELO, then K is 4. H might be 1000, E is 00, L is 00, O is 0001.
Got it. A vector with a single one.
Yep. So for the input hell, you'd feed the vector for H, then the vector for E, then the vector for L into the RNN step function, one after the other.
And after processing L, the RNN spits out an output vector.
Yes. And that output vector will have, in this case, 4 numbers. We interpret those as the RNN's confidence or log probability for each character, HELO being the next one.
And the goal is to make the number corresponding to the actual next character, in this case the second L, as high as possible.
Exactly. And the numbers for H, E, and O should be low.
How do you adjust the weights to achieve that? Backpropagation again?
Yep. You calculate the error, how far off the predicted probabilities were from the target, which is essentially a probability distribution with 100% on the correct next character. Usually done with a softmax layer on the output and a cross-entropy loss function.
Softmax turns those raw scores into probabilities that sum to 1.
Correct. And cross-entropy measures the difference between the predicted probability distribution and the target one. That loss value then gets backpropagated through time. Yeah, back through the recurrent connections, step by step, to figure out how to adjust all the weights, WEST-Y, and the LSTM gate weights, to reduce the error. Optimization algorithms like RMS-prop or ATOM handle the weight updates.
Wow, okay, so it's constantly learning, when I see the sequence, this character is more likely to come next.
Precisely. And crucially, because of that recurrent hidden state, it can learn context.
Yeah.
It learns that the first L in hello is usually followed by another L. The second L is followed by O.
It has to use its memory, its hidden state, because the input bell is the same both times.
Exactly right. The hidden state captures the
Okay,
context.
okay. So you train this massive model. It learns all these character sequence probabilities. How do you actually generate new text?
That's the fun part.
Yeah.
At test time, you give it a starting character, maybe a seed sequence like the
Mm,
Matterlake.
okay.
You feed that character or sequence into the trained RNN. It processes it and outputs a probability distribution over all possible next characters.
The probabilities it learned during training.
Yes. Then, instead of just picking the single most likely character, you usually sample from that distribution.
Sample. Like roll a weighted die.
Kind of. If A has a 40% probability and B has 30%, you're more likely to pick A, but sometimes you'll pick B or other less likely characters. This has randomness and creativity.
Okay. So you sample the next character. Let's say you pick N.
Right. Then N becomes the input for the next time step. You feed N into the RNN, it updates its state, gives you a new probability distribution.
And you sample the next character from that.
And you just keep doing that. Feed the previously generated character back in as input, get probability, sample the next character, repeat.
It just goes generating one character after another based on its learned probabilities and the sequence it has generated so far.
Exactly. Like a chain reaction, guided by the learned patterns.
That is surprisingly simple conceptually, but obviously powerful. Now, the source had some amazing examples of what happens when you train these on different data sets. Let's talk about those. Paul Graham's essays first. Only 1 milli of text, which seems tiny.
It really is quite small, yeah. And they used a 2-layer LSTM, 512 hidden nodes, maybe use some dropout during training to help it generalize better.
And the text it generated, it wasn't Paul Graham, but it sounded kind of like him sometimes. And it learned punctuation and stuff.
Yeah, it learned English structure, commas, periods, even made up citations like all from scratch, just characters. Sometimes you'd get these almost profound-sounding snippets like accompanies a meeting to think to investors. Mostly nonsense, but interesting nonsense.
And this temperature thing for sampling. Lower temp means more predictable, higher means more wild.
Right. Temperature scales the probabilities before sampling. Low temperature makes the highest probability character even more likely, leading to more conservative, sometimes repetitive text, like that infinite loop on startups it got stuck in.
Huh. Right.
High temperature flattens the distribution, making weirder choices more likely, more creative, but often more mistakes, less coherence.
Finding the right temperature is like tuning the creativity knob.
Hmm.
Okay, next, Shakespeare. Bigger data set, 4.4 MB, 3-layer RNN.
And here, the results got even more structured. It generated dialogue, with speaker names it made up, like Pandarus, followed by lines. It learned the format of a play.
Just from character sequences, that's nuts.
It is pretty amazing. Again, not real Shakespeare, but it often captured a vaguely plausible style and structure, sometimes surprisingly coherent little monologues.
Then Wikipedia.
Yeah.
Huge data set, 96 MB, and it started learning Markdown.
Yeah. Generated text with markdown links, even hallucinated URLs that looks plausible. It learned to open and close parentheses and brackets correctly most of the time.
Wow.
It even generated fake XML snippets with properly nested tags. It's learning these complex syntactic rules just by observing patterns.
Okay, the algebraic geometry one, trained on LaTeX source, this blew my mind. It generated LaTeX that almost compiled.
Astonishing, right? LaTeX has such a rigid, complex syntax. The model generated stuff that looked like real math definitions, theorems, proofs.
He even tried to make diagrams, and that proof omitted slide is hilarious.
It really is. It shows the power and the limitations. It gets the structure mostly right, but sometimes makes mistakes like mismatching begin proof with end lemma. Small errors that break compilation, but the overall form is learned.
And finally, Linux source code. Nearly 0.5 GB of C code. Huge models, trained for days.
And the generated code, again, wouldn't compile probably, but it looked like C code. It had comments, function definitions, its statements for loops, correct brace usage, indentation.
Using pointer notation and stuff correctly?
Mostly, yeah. Common errors were things like using variables that weren't defined or having a function declared void try to return a value, semantic errors. But the syntax, the shape of the code, was often remarkably good.
And it sometimes just started spitting out the GNU license.
Ah, yes, or a bunch of hashtag include statements. It clearly learned those common boilerplate patterns appear frequently at the start of files.
Just incredible pattern matching. Oh, and the baby names one. Trained on 8,000 names and it came up with new ones.
Yeah, some plausible, some funny, like Killy, Char, Armor, Mars, Arbor. It learned the phonotactics, the sound of names, and generated new combinations. Could be a weird inspiration tool.
Definitely. Okay, so we see these amazing end results, but how does it learn? The source looked at samples during training, right? Using War and Peace.
Yes, that's super insightful. At the very beginning, like iteration 100, it's just random characters. Total mess.
Right.
By iteration 300, you start seeing spaces separating clumps of letters. It's learning word boundaries. Then maybe basic punctuation.
Okay, structure first.
Then around iteration 500, short, common words start appearing. The, a, and.
It's learning vocabulary.
By iteration 700, more English-like text, longer words.
Mhm.
By 1200, it's using quotation marks, names start popping up. By 2000, it's generating mostly correctly spelled words, more coherent sentences.
So it learns structure, then short words, then longer words, and the longer range meaning comes last.
Seems that way. It builds up complexity layer by layer.
And the other cool thing was visualizing inside the network, looking at neuron activations.
Yeah, for the Wikipedia model, they looked at the hidden state. For a given input sequence, they'd pick a random neuron, or cell in LSTM terms, and see how excited it was, its activation value, at each point in the text.
And they found cells that seemed to have learned specific jobs.
Some did, yeah. Like one cell that consistently got excited whenever the input text was part of a URL.
Wow.
Another that lit up only when inside markdown double square brackets.
So it learned to track markdown state.
Another cell seemed to vary linearly inside the brackets, almost like a counter. And one turned off sharply right after the first WDU in www.
That's incredibly specific. So these individual units are learning meaningful little algorithms or detectors?
Some seem to be, yes. Though it's important to say the representation is distributed. Many cells are probably doing complex things we can't easily interpret. But the fact that some learn these clean, interpretable roles is fascinating. Maybe 5% or so showed these clear patterns.
And the model wasn't told to track URLs or brackets. It just figured out that doing so helps predict the next character better.
Exactly. That's the beauty of end-to-end learning. The network discovers useful internal representations and computations just from the raw data and the simple objective of predicting the next character.
It spontaneously learns to, track whether it's inside a quote or not. That is just fundamentally cool.
It really is a powerful demonstration.
Now, for folks listening who think, I want to try this, the code is out there.
Yeah, the source mentions the charting code is on GitHub, MIT licensed. You feed it a big text file, and it trains a model. Though they warn, you probably want a GPU. Training takes time.
Right, lots of computation.
And there's also a simpler, like a 100-line Python script using just NumPy that demonstrates the core RNN mechanism if you want to understand the guts without a big library.
Good starting point. So wrapping it up, this magic of RNNs generating text comes down to processing sequences, having this internal memory or state, and learning statistical patterns through, well, lots of examples in backpropagation.
That's a great summary. They learn to predict the next step based on the journey so far.
And it feels like we're just scratching the surface. This is clearly a super important area in AI.
Absolutely. RNNs, LSTMs, and newer variants like transformers, which build on these ideas, they're fundamental to so much of modern AI, especially in language. Huge amounts of innovation still happening.
And that final meta point was great. They trained an RNN on the blog post about RNNs.
Aha, yeah.
And the generated text was all about how great RNNs are.
The model quickly latched onto the main theme, a funny feedback loop.
Perfect. And hey, if you want to go even deeper, check out the original source for links talks, discussions, people training RNNs on recipes, rap lyrics, political speeches, even folk music notation. Lots to explore.
Definitely encourages you to play around with it yourself. See what patterns you can find in your own data.
Well, this has been incredibly insightful. Really demystified some of that RNN magic, though it still feels pretty amazing. Thanks for breaking it down.
My pleasure. It's fascinating stuff and, yeah, always more to learn. Maybe someone listening will train the next viral character model.